Right, so we're given the line L and with those parametric equations, and we asked to firstly show that L lies on this plane. That's not a difficult thing to do. We are asked to show that L is parallel and it lies below the plane 5x minus 3y plus 3z equals 1. And we are asked to show that L is also parallel to and below the plane 6x 2y minus 2z equals 3. Alright, now I just have to apologize. There is a typing error here. That should be above the plane. Okay, so let us just fix. Alright, so we can take A, we can easily solve that. So to check that it lies on the plane, right, so we're just going to make sure it satisfies the plane equation. So you can see that, you can very easily see that 4t minus 4z is equal to 0. Alright, hence that whole line, the line where x is equal to 0, y is equal to t, and z is equal to t, right, it satisfies the equation 6x plus 4y minus 4z. Okay, right. Thus, L lies on P, where P is that plane there. Okay. Now we are asked secondly to show that L is parallel to and below that particular plane. Right, so to do the first part, right, so note that the normal vector for the plane P, the normal vector for that particular plane P, normal vector for that plane we know is 5 minus 3 plus 3. Okay, and that is there. That's the plane P we're talking about. That's the plane P we're talking about. Now, we want this line, we want to check if this line is parallel to this plane. Now, how do we know that this line is going to be parallel to that plane? Alright, so this is, again, so what you do is here is you pick your line L. There's my line L. Okay, and okay, so we can pick a point on that line there. Let's call it, let's just pick T to be 1. And let's pick T to be 0. Okay, so those are 2 points on the line. And now I'm looking at the vector. I'm looking at the vector, that vector there. And we'll call that vector alright, so we'll call the vector QR, or rather RQ. The vector RQ is the vector 1, 0, 1, 0, 1, 1. Okay. Okay, so you can take the vector RQ and you can take the dot product with NP. And you can easily see that if you take the dot product between those two vectors, it's clearly 0. Okay, so hence this line is parallel to the plane P. If you have the plane there and you want to check that this straight line is parallel to that plane, remember the plane is I have my normal vector to the plane, okay, and basically for the line to be parallel, I want this normal vector that I have for the plane, I want it to also be orthogonal to a vector on that particular line. So I've just shown that basically this vector here, I've shown that it's orthogonal to this vector that I talked about there. Okay, so therefore the line is parallel to the plane. Okay, now next we are asked to show that this plane lies above the line. So I quickly did a sketch here. So this is the plane we're talking about here. Okay, this is just a section of the plane. Okay. And if we look at our line, that is the line that is my line there. Okay, now okay, so how do we check? We already know that this line here is parallel to the given plane. Okay, and you can now see by inspection. You can see by inspection this vector here that we're talking about there. That vector, let's call that vector u. That vector there is the vector 0, 0, third. Okay, and that vector points in the direction of the positive z-axis. Okay, so that clearly, by looking at that vector, you can see that the plane is above the straight line because that vector points up in the positive z direction. So it's clear from there that the plane, given plane P, is above the line L. Right, next we're asked to show that the line L is parallel to this plane here. Okay, and again we call that plane P. Okay, and remember I said above, the line is above. Okay, so now this is the same procedure again. So you can again take your line. All right, so you take your line, the one that we talked about previously, this one here. Again, the same vector, and note. All right, so note that we said that the normal vector for the plane P is the vector 6, 2, minus 2. And so how do we check that a line is parallel to a plane? We need the normal vector of the plane to also be orthogonal to a vector on the straight line, which in this case is our vector RQ. So again, it's a straightforward procedure. So you take the vector NP and you take the dot product and you see what happens. So you take it with that vector there, and it's easy to verify there. You get the vector 0, 1, 1. You take the dot product with the vector 6, 2, minus 2. and that is equal to 0. All right, and you can quickly make the conclusion then that L is parallel to P. Remember, we want the normal vector to also be orthogonal to the vector on that straight line. So therefore, the straight line is parallel to the plane. All right, next, if you quickly go and draw a little section of the plane and you look at your straight line, you can very easily see there's our plane, P. Okay, there's that section which lies below the XY plane. And again, we've got our straight line. We've got our straight line there. Okay. And because the plane is parallel to the line and the plane are never going to intersect, and the distance is going to stay consistent. And here, if we look at this vector here, one can clearly see there, if we call that vector u, that vector points in the direction of the positive z-axis. So therefore, the line is clearly going to be above the plane. Right, so that concludes question 1. Let's move on to the next question. Okay, so the question asks, find an equation for the plane that contains the line x equals -1, 3t, y equals 5 plus 2t, and z equals -2 minus t, that is perpendicular to the plane, 2x minus 4y plus 2z equals 9. Okay, so, right, so the line, so basically the line is this line here, is the line x equals -1 plus 3t, y equals 5 plus 2t, and z is equal to -2 minus t. So that's the parametric equation of that particular line. And so we're working with right, so we're working with that line there, and you can take 2 points on that line, call that point -1, 5, and -2. So it's just where t is equal to 0, and where t is equal to 1, the other point is going to be 2, 7, minus 3. Okay, right. So there you've got your 2 points. Call that P and Q, and that's the line L. Okay, and you got P by making T 0, and you got Q by making T 1. All right, and now we've also got the plane. Let's call the plane R, and it's the plane 2x minus 4y plus 2z is equal to 9. All right, and you can write that as 2x minus 4y plus 2z minus 9 over 2 is equal to 0. So the normal vector of this plane R is the vector 2 minus 4 plus 2. All right, so we want to find the plane that contains the line L and is perpendicular to the plane to the plane R. Okay, so we just note that the vector PQ. So I want the plane to contain this line, and essentially I want the plane to contain the vector PQ, which is the vector 2 minus minus 1, which is 3, 7 minus 5, which is 2, and minus 3 minus minus 2, which is minus 1. Right, so if you want to look at it geometrically, if I want to find a plane that's perpendicular to another plane, so if I take the plane there and I want to find the equation of a plane that is perpendicular to that plane, then, all right, geometrically, it's going to look something like this. Okay, now for me to find that plane, I first of all need to find a normal vector there with any plane, and then I have to also find a normal vector of, okay, so this, let's say that's the given plane, and this is the plane I want to get that's orthogonal or perpendicular. Okay, so for me to find the equation of this plane, I need to find a normal vector there. So the normal vector is basically going to be a vector that looks like that. And that vector has to be orthogonal to the normal vector of this plane, which I'm gonna of this plane here. Right, so that vector there is the normal vector of this yellow plane. Okay, and now I want to find the normal vector of this plane that's orthogonal. And so I need to find a vector that's orthogonal to the normal vector of the yellow plane, essentially. All right, so I'm going to just take that sketch there, and I'm just going to place it there for the time being. All right, so what I'm going to say is let's just let S, all right, be the plane that contains L and is perpendicular. It's perpendicular to the plane R. Okay, now note that let's call the normal vector of this plane S. Let's call that the normal vector. The normal vector is such that two things need to hold. The normal vector S needs to be orthogonal to the normal vector of R. Okay. That's one, and two is the normal vector of S also needs to be orthogonal to the vector PQ. Okay, and remember we said PQ is that vector there, because remember we want the plane to contain that line, and so the normal vector has to be orthogonal to that vector as well. All right, okay, so carrying on. Okay, so we can set up two equations 1 and 2. So you've got, so basically you can continue in S, the vector ABC, and you need that with the vector in R. You need the dot product with that vector to be 0, which is basically 2a minus 4b plus 2c, that needs to be 0. That's one equation. I mean, yeah, there are other ways of doing this as well. And you also need this equation, the dot product with PQ. Now we work the PQ vector out as that. Okay, and that has to be 0, so that's going to be 3a plus 2b minus c is equal to 0. So that's my second equation. Okay, so this basically that implies that you can take twice equation 2 and you can add it to equation 1, which is going to lead to, if you take, okay, so that becomes 8a, the b's cancel out and the c's cancel out, and you're basically left with that, and that implies that a is 0. Okay, and from there, we can then say from 1, we can say then that that c is equal to 2b. Right, so basically you can let this normal vector that you have for the plane S, you pretty much can pick any value for B and C that you want. It's basically, you can pick X as 0. You can pick B as 1. And you can pick C as 2. All right, so that's a sufficient vector you can use. All right, and then if you go back to the sketch on the previous page, if we go back there and we take that line there, remember, so the equation of the plane becomes, so equation of S becomes, so the equation of S becomes, so what do you want? Let us choose an initial point. For a plane you always need an initial point. Okay, let's choose that point there as our initial point. So our initial point, we're going to start with X there. What's the initial point there? Minus 1. Okay, then we have our Y. Our Y is going to be minus 5, and our Z is going to be minus 2. You're going to equate that everything to 0, and what does your normal vector become? It's the vector 0, 1, and 2. Okay, so the final equation of my plane becomes y minus 5 plus 2z plus 4 is equal to 0. So the plane that we are talking about here is the plane y plus 2z equals 1. All right, so that is the plane that contains this particular line and is perpendicular to the original plane. So remember, the important thing here is we want for two planes to be perpendicular. Remember, you want the normal vectors must also be perpendicular to one another. So if two planes are perpendicular, their normal vectors need to be perpendicular. And if two planes are parallel, their normal vectors need to be parallel. All right, so they ask us show that these 4 points lie in the same plane. Okay, now how would we do this? Well, geometrically what we want to do is to show all those 4 points lie in the same plane. You need to basically show that there's a vector that's orthogonal to the following vectors, which I'm going to draw just now. So you are given, right, so you're given these points. So you're given the point, there you're given the point 2, 0, 1. You're given the point, you're given the point -1, -2, and -3. You're given another point there, -2, 0, 1. And you're given a third point there, -4, -1, -1. Okay, and you're basically looking at these vectors here. Okay, and I'm going to call this vector u, I'm going to call this vector v, and I'm going to call that vector w. So now geometrically, what I basically want here is the following. Okay, so I want a vector there that is orthogonal to that vector. It is orthogonal to that vector, and it is orthogonal to that vector there. Alright, so I want to just basically write the vectors down. So that is going to be the vector -3, -2, -4. V is the vector -4, 0, 0. Okay, and the vector W is the vector -6, -1, -2. Okay, so let n be the vector orthogonal to u, v, and w. Okay. Okay, let's see if we can find this vector. Now, for those of you that have looked through the work in chapter 3.5, you can use the cross product as well, or you can just you can be a little bit intuitive, and you can do it without the dot product. So this vector, let's call it a vector x, y, z, and we'll go find values for x, y, and z. All right. Okay, so because n is orthogonal to v, we need. All right. Okay, so as v's dot product with n needs to be 0. Right. So we can pick. So we can pick x as 0. All right, so thus that works well. Okay, now we just need to go and pick values for y and z. Now, as n's dot product with u is 0, we need. Right, we need what? We need u's dot product with n. We need basically we need 0, y, z dot product with -3, -2, -4 to be 0. Okay, so that then implies, if we carry on, from there we need -2y, -4z to be 0. So you can parameterize parameterizing, we get that this vector, you can let this vector be 0. You can make yt, and if you make yt, then z is minus a half of t. Alright, so where t is a real number. Right, so completing, right, so you can, let me just fix that. So you can take the dot product of n with w, and you get this, minus 1, minus 2, and let's just see if this vector is in fact orthogonal to the vector n. Right, so that then basically becomes minus t plus t, which is equal to 0. Alright, hence the 4 points, they lie in the same plane. Okay, so guys, you could have also used what we learned in section 3.5. You could have checked the scalar triple product. You could have used the scalar triple product as well. Alright, next we are asked to find the distance. Find the distance between two planes, plane 1 and plane 2. Now this isn't difficult to do because you can apply that distance formula that we talked about. So all you do is, right, so you have your plane 1, which is this plane here. And you've got the plane P2. Right, so I mean, you start off with, you can pick a point on the second plane. You can write that second plane as 6 x minus a half minus 8y. Okay, and you can write that as 2z minus 0 equal to 0. Okay, so we can pick the point P as a half 0 0 on P2. Okay, and now we can find the distance between P and the plane P1. Alright, so the distance between P1 and P okay, let's call it D, is, so the distance is, we said the distance is the absolute value of 3.5 minus 4 0 plus 1 times 0 minus 1 divided by the norm of the normal vector of P1. And that is the square root of 3 squared plus minus 4 squared plus 1 squared. Okay, so that then you can simplify that then to 3 over 2 minus 2 over 2 divided by the square root of the 9 plus 16 plus 1, which is 26. And so basically the distance becomes 1 over 2 square root 26. Okay, so the distance between the two planes is 1 over 2 times square root 26 units. Okay, so the point is just you choose a point on the one plane and then you work out the distance between that point and the other plane. Now just a quick note, you can see that these two, you can see it by inspection. You can basically see by inspection that these two planes are parallel, okay? And you can see that by comparing the normal vectors. You can see here that this normal vector 6 minus 8, 2 is basically a half of, well, it's basically, compare these two vectors, the one vector is twice the other vector. So basically the one is a scalar multiple of the other. So their two normal vectors are parallel, and this means that those two planes must be parallel.